Okay, so let's talk about some models of acceleration and velocity with differential equations. So let me get the simple one out of the way. This is probably the one you're most familiar with. It's just that the acceleration of gravity is constant. So for acceleration, I chose to write the derivative of velocity. Of course, that's the same as acceleration. And I'm going to set this equal to negative g. So, of course, the acceleration of gravity is in the negative direction. So if I consider g to be a positive number, I want to put a negative in front of it. Of course, g is this familiar number. It's the acceleration of gravity, which we often just use 9.8 meters per second squared, or it's about 32 feet per second squared. And this ignores some things that may or may not be important. Like if your object is not moving too fast or too far, then this is a decent model. But if it's moving very fast, then maybe you should keep track of air resistance, because this ignores air resistance. Also, this ignores the effect of traveling long distances, because the truth is gravity is stronger or weaker depending how far apart two things are. So if this is just the acceleration of gravity on Earth, so maybe I'll talk about Earth. This is the acceleration of gravity when you're near the surface of the Earth. If you're going to be falling from way up high in the sky, then gravity is going to be weaker up there where you start. So this ignores the effect of long distances, I would say. So let's talk about those things. We're going to pay attention to these one at a time. I'm not really going to write down an equation that takes into account both air resistance and the fact that gravity changes depending on distance. We'll do these one at a time. So let's say I just want to keep track of air resistance. Air resistance, roughly speaking, it introduces a force that's about proportional to the square of velocity. And, of course, air resistance is just in the opposite direction of whatever you're traveling. Like air resistance has the effect of slowing you down, whether you're moving up or down. So if velocity is positive, air resistance is going to introduce a force in the negative direction. And of course, force is mass times acceleration, and we're assuming the object that's falling has a constant mass. So if force is proportional to the square of velocity, then acceleration is also proportional to the square of velocity. So I just introduced a term because this is acceleration, and I should introduce a term that goes in the opposite direction. So if v is positive, it's going to go in the negative direction, and it's proportional to the square of velocity. So that's this. So it went from this to this. Of course, if I'm in the downward direction, then the air resistance is pushing up, so I flip this from a minus to a plus. And if I want to unify these two things, it's a little bit awkward, but I could call this V times the absolute value of V, which works, whether V is positive or negative. This matches whichever one it's supposed to match. Anyway, this is separable. I'm not going to solve it right now, but these, however you want to write it, of course, it's awkward with the absolute value. I would prefer to either strictly do the V positive case or the V negative case, just because I don't want to deal with a formula that has absolute values on it, but it is separable either way. So it can be solved. Let's talk about terminal velocity, because this is something that you really don't see with the simple model. According to the simple model, if I drop something, it's just going to keep falling faster and faster and faster until it hits the ground. But that's not that's one unrealistic thing about the simple model. There is such a thing as a terminal velocity in real life. If you're falling a long distance, you're really not going to go faster and faster without bound. You pretty much hit a velocity that you're never going to fall faster than that. So what we're talking about is actually an equilibrium solution to the differential equation. It's like when velocity hits a certain constant value, it just sort of levels off. So how do I find that? I take a differential equation, and by the way, this happens when you're falling down. When you're on your way up, you're not going to hit a terminal velocity. In other words, you're not going to hit a velocity that you just sustain that's a positive velocity. As long as you're on your way up, gravity's going to keep slowing you down, and so you're falling up, you're going up slower and slower, and then you start going down. So terminal velocity is relevant for the negative case. So I'm going to find an equilibrium solution for the negative case. And how do we do that? We set whatever this is equal to 0 and solve for v. So it's going to be really easy. I'm just kind of... This is an excuse for me to talk about things. We set this equal to 0 and solve for v. Let's see if I can actually do this right. G over K. Great. So, of course, yeah, G is the same G from up here, and K is some constant that has to do with, you know, the details of the problem. Like, air has a certain density, but depending on what your object is, whether it has a lot of surface area or whatever, K could be bigger or smaller. And depending on the shape of your object and its density and surface area and stuff, it will have a different terminal velocity. It depends on K, but there it is. So let's talk about the other thing, which is the fact that gravity is actually stronger or weaker depending on how far two objects are from each other. So here's Newton's law of gravitation. G is like a universal constant. Capital M and little m are the masses of the two objects. Of course, for our example, we're probably talking like big M is just the mass of the Earth, because the Earth is one of the objects. And little m is the mass of whatever little object I'm throwing up in the air or dropping off a building or whatever. And little r is the distance between the two masses. So if your object isn't falling too far, then little r is basically just the radius of the Earth. And if you're 10 feet above the surface of the Earth, that's about the same as being, in the big scheme of things, that's about the same as being on the surface of the Earth. So if you're not falling too far, little r is a constant. But if you are, then you have to keep track of this. Anyway, let's write a differential equation. So force is mass times acceleration, and r is playing the role of position here. It's like how high I am above the surface of the Earth, or my distance from the center of mass of the Earth, I should say more properly. So this is mass times acceleration. Acceleration is r double prime. And I set that equal to this. So r double prime equals this. So actually this is a second order differential equation. We haven't talked much about these, but we can reduce it to a first order using a substitution trick. So this r double prime is a derivative with respect to time. So one way of describing this is r double prime is dv over dt, because it's acceleration, so that's the derivative of velocity. dv over dt I can write in this funny way. Of course, this is just the chain rule. We can imagine canceling the dr's, but we're not really supposed to do that, but that's how I remember the chain rule, is that if I canceled them, I would get the same thing. And meanwhile, okay, so dr over dt is v. So, right, v is the derivative of position, so that is v, and this is this. So I can rewrite this differential equation because r double prime is v dv over dr, so I write that equals this same thing. Now it's not a second order differential equation. With this substitution, this is now a first order. I see just a derivative. This is not a second derivative. And my variables are v and r, and we've eliminated t. So it's a bit of a funny substitution. But this is now separable. So I keep my v on this side with the dv, I move my dr over there, I call this r to the minus 2 when the variables are separated, and I integrate both sides. This side turns into this. Integral of r to the minus 2 turns into an r to the minus 1 with a negative sign to cancel this negative sign. I use some initial conditions. Let's assume that in the beginning, v is v naught and little r is some value we'll just call big R. And I can use that to solve for c. So this is the result of me just plugging in v naught there and big R there, and then getting this over and solving for c. That's that. And yeah, sorry, I made a couple of mistakes here. This used to say a plus, but I crossed it off and wrote a minus. So there's a little bit of mistakes here that I fixed. So, right, where am I going with this? I'm just sort of messing around solving this differential equation. Let's try to answer a question. So we're going to talk about what we call escape velocity. Because if you fire an object fast enough, then, like I was saying, the force of gravity becomes less and less as it gets farther and farther from the Earth. And if you fire it fast enough, then it's not going to slow down that much, and it's going to get really far from the center of the Earth where the pull isn't so much, and it can actually go forever. And fast enough, quote unquote fast enough, is what we call the escape velocity. So we're just going to talk about that. Say we fire an object upward. That means, of course, little r increases because little r is the distance between the two masses, and this object is getting farther and farther from the Earth. So my v, which I just solved this for v, of course, solving this for v involves getting the 2 over, but also doing the square root. And maybe when I took the square root, I should write plus or minus, but we're imagining that we fired this object upward, and we're trying to figure out what is the initial velocity that keeps it moving upward forever. So I'm going to take the positive square root. So I take the positive square root, I solve this for v, and of course I put in this c value there, so that's there. And little r, as we just discussed, is increasing as long as this is moving upward. As long as v stays positive, little r is increasing. And this is r to the minus 1, so this term just gets smaller and smaller. Like little r gets bigger, this term gets smaller. In fact, as little r goes to infinity, this term goes to 0. So if I just cover this up with my finger, I get this. So my velocity is always going to stay at least this value. Again, assuming that it keeps moving upward. If it stops moving upward, then I need to talk about v that has a negative sign in front, because I should have taken the negative square root. But as long as it keeps moving upward, it's going to be at least this. So if this is a positive value, then there's no way for v to ever hit 0 and then go negative again. In other words, so what makes this a positive value? Well, v naught squared needs to be bigger than this number, so v naught needs to be bigger than the square root of this number. And that's what we call the escape velocity. If your initial velocity v naught is at least this number, then the object, it will escape the gravity of the Earth, so to speak. It will keep positive velocity forever.